Now we're going to take a look at the two related distributions of the Poisson distribution and the exponential distribution. Again, remember that the Poisson distribution helps find the probabilities of the number of events. And we wish to know, say, the number of times customers come into the store or the number of cars crossing an intersection. Again, since this is a count type of data, we're going to use the Poisson distribution for this. Exponential distributions, recall, will focus on the time of arrival between events. For example, the average time between customers' arrival in a store or the average time cars cross a bridge. So the Poisson distribution is a discrete distribution, again, focusing on count data. And the counts are, in this case, let's say a number of customers entering a store. We have this on the right. So we have 9 weeks of data, or 63 observations. Only 2 weeks are actually shown on the right. And what we've done is we've calculated the mean of the 63 observations as being 5.301. If we use the Excel function Poisson.DIST, with k being the number of events and mean being the average for the data set, and again true, providing the cumulative probability, false if we wanted an exact probability of k events, we would get the following. If we wanted to ask the probability of less than or equal to 4 customers, we do Poisson.DIST 4, 5.301, and true. And this will tell us that it is 0.3893, or a 38 or 39% chance of getting less than or equal to 4 customers. Now, if we were looking for the probability of getting exactly 5 customers, we would use the Poisson.DIST 5 for k events, 5.301 for the mean. We put false for the cumulative, so it won't be cumulative, and we will get a 0.1739, or a 17% probability of getting exactly 5 customers. If we're looking for probability of greater than 6 customers, then what we do is we are going to first look for the distribution, the Poisson distribution of getting 6 customers or less. So that would be the Poisson.DIST 6, 5.301, and then true. Now, that will give us 6 or less. So what we want is, since we want greater than 6, we would do 1 minus that, and that'll give us 0.2839. If we were looking for the probability of between 4 and 6 customers, what we'll need to do is we'll need to find the probability of getting 6 customers or less, which is what we had done before, and that gave us 0.716. And then we need to get the probability of getting less than or equal to 3, because we wouldn't do the Poisson.DIST with 4 because that would give us 4 or less. We want to include 4 in that. So we're going to drop that by 1 and look for the probability of getting less than or equal to 3. And therefore, we use Poisson.DIST 3, 5.301 as the mean, true. That gives us 0.225. When we subtract the 2, we will end up with 0.491, or 49.1% probability of getting between 4 and 6 customers. Now remember, that's almost 50%. Remember that we had said that the mean, or the expected value, was around 5.3, which is right in between this. And so we would expect our expected value to be roughly in the middle of this, and this is where we get a large percentage, or 50% of the population, or 50% of the counts. So now let's look at the exponential distribution. Again, this is a continuous probability distribution. It's related to Poisson, but it focuses on the arrival times rather than the actual counts. So we're not looking at count data. It is continuous. Where would we use this? Well, assume we're at a theme park and we want to know the distribution of arrival times to a queue. On the right side, we have some arrival times to the queue of customers, and with a mean of mu and an arrival time of 3.57 minutes. So in order to use the exponential distribution, we will have to provide a rate, which is lambda, and lambda will be equal to 1 over mu, the inverse of the mean. Now, what we have to do is, since we're calculating the arrival time differences here, or the arrival times between customers, you'll notice that on the right we have the exact arrival time of the customers in minutes, but we have created a delta column, which will say that the first person came in at 1.45 minutes, the next one came in 1.14 minutes later, the next one 1.09. So it's important to do that. And when we use the Exponent.DIST function, it's going to give us, again, the probability of the arrival time given our expected arrival times with a cumulative probability of true, a cumulative probability as true. Taking this example a little bit further, we can see that if we are, again, using that same set of data with 100 observations, we have our mean of 3.57. We calculate our rate as 1 over the mean, which is 0.28. Our probability of arrival time being less than or equal to 2.5 minutes would be Exponent.DIST 2.5, comma, and then we put in our rate, which is 0.28, and we do true for our cumulative probability, and that will give us a 0.504 result. The probability of exactly 3.1 minutes is going to be a little bit different because it's going to give us, again, Exponent.DIST 3.1, comma, 0.28 for the rate, and then we put in false, and there is a 13% chance that we're going to have exactly 3.1 minutes. So if we have the probability of greater than 4.9 minutes, again, we're going to have to do that trick where we did 1 minus, in this case, 1 minus the exponential distribution, 4.9, 0.28 as the rate, again, true for the cumulative probability, and we will obtain a value of 0.253, so 25.3% probability of being greater than 4.9 minutes. And again, if we wanted to do something in between, the probability of, say, over 1.7 minutes but less than or equal to 4.2 minutes, we will use the functions Exponent.DIST 4.2, comma, 0.28, comma, true for the cumulative distribution of the arrival time of 4.2 and everything less, minus the exponential distribution of 1.7 minutes, comma, 0.28 rate, comma, the cumulative distribution true. So it will subtract those two and give us a 0.312 or 31.2% probability of being between 1.7 minutes or greater than 1.7 minutes, but less than or equal to 4.2 minutes.